The universe holds secrets that could shatter our understanding of reality. We are surrounded by cosmic territories where the fundamental laws of physics break down, regions so strange they challenge everything we think we know. By the end of this journey, you will see the cosmos through an entirely new lens, uncovering 23 of its most profound mysteries. We will explore why entire galaxies are being pulled toward an invisible force, and what causes billion-light-year-wide voids of absolute nothingness. These are not just empty spaces but active frontiers where reality itself unravels. What single cosmic mystery do you believe could change our future the most? Our own galaxy is racing through space at over 1,000,000 miles per hour, pulled by a force we cannot see. This is the Great Attractor, a gravitational anchor point in the cosmic ocean, located in the direction of the Centaurus constellation. It does not merely tug at our Milky Way, but at an entire swarm of galaxies in our local supercluster, all flowing toward a single, invisible destination. The problem is, we are trying to look directly at its heart from behind a cosmic curtain. This curtain is our own galaxy's bright, dusty disk, an area astronomers call the zone of avoidance. It is like trying to see a distant city while standing in the blinding glare of your own hometown. For decades, this zone blocked our view, leaving the core of the Great Attractor a complete mystery. Astronomer Dr. Renée Cron-Courtoueg and her colleagues have dedicated their careers to peering through this veil. Using telescopes that can see in infrared and radio wavelengths, which cut through the dust, they have begun to map the hidden structure. What they found is not a single, monstrous object, but an immense supercluster of galaxies, one of the most massive conglomerations of matter in our observable universe. Yet, even this vast collection of normal matter does not fully account for the staggering gravitational pull we observe. This forces a profound question. What is generating the rest of that force? The leading theory points to an immense concentration of dark matter, the invisible scaffolding of the cosmos, woven through the supercluster in a way we have never seen before. This hidden core challenges our very models of how matter, both seen and unseen, is distributed across the universe. It reveals that the largest structures are still largely unknown to us, pulling our gaze from this immense gravitational sink toward its opposite, a void of staggering emptiness. Yet if the Great Attractor represents a colossal concentration of mass, its polar opposite exists as a staggering emptiness. The Eridanus Supervoid is a cosmic desert so vast it defies comprehension, a billion-light-year-wide region of near-total nothingness. Picture our observable universe as a bustling metropolis. This void would be a vacant expanse larger than any continent, a place where galaxies are almost entirely absent. It is not merely an empty patch of space, but one of the largest single structures ever identified. Its discovery did not come from spotting an absence with a telescope, but from hearing its echo in the universe's oldest light, the cosmic microwave background. This remnant glow from the Big Bang is remarkably uniform, like a smooth canvas, but it holds a mysterious cold spot, a patch of sky significantly chillier than its surroundings. For years, cosmologists struggled to explain this anomaly. The leading theory suggested the cold spot was an artifact, a trick of the data, but further analysis pointed to a shocking cause, the Eridanus Supervoid. How can a void create a cold spot? As light travels across the universe, it gains energy falling into gravitational wells, like clusters of galaxies, and loses energy climbing out. This is the integrated Sachs-Wolf effect. But light passing through a vast void experiences the opposite. It loses more energy entering the underdense region than it gains leaving it, resulting in a net energy loss that we observe as a colder temperature. The problem is the sheer scale of the void. According to our standard models of cosmology, a void large enough and empty enough to create the observed cold spot should not exist. It is statistically improbable. A cosmic anomaly that challenges the principle that matter is distributed fairly evenly across the universe on the largest scales. This has led to radical explanations. Cosmologist Laura Mersini-Houghton has proposed a theory that this void is the imprint of a cosmic collision, a bruise left on our universe from a gravitational tug of war with another universe in the multiverse. While this remains highly theoretical, the supervoid itself is very real. Its existence forces us to question what violent or exotic processes in the early universe could have carved out such an immense bubble of nothing. Does it point to a flaw in our understanding of cosmic inflation, the period of rapid expansion just after the Big Bang? This vast emptiness is not passive. It is an active puzzle that questions the very uniformity of space, guiding us from this profound cold toward a source of inexplicable heat. From the profound cold of one void, we journey to another, an even greater expanse of nothingness known as the Boötes Void. This is a region of space so empty it has earned the name the Great Nothing, a spherical chasm spanning an almost incomprehensible 330 million light-years. If you were to place our Milky Way at its center, the nearest major galaxy would be millions of light-years away in every direction. Within this staggering emptiness, astronomers have found only a sprinkling of galaxies, perhaps 60 or so, where standard models predict thousands. They shine like solitary lighthouses in an infinite, dark ocean, each one a profound mystery. Astronomer Robert Kirshner, who helped confirm the void's existence, noted how its sheer scale and emptiness directly challenged everything we thought we knew about how the universe structures itself. The greatest puzzle is not just the void itself, but the galaxies trapped within it. They are not strange, twisted relics. They are, by all accounts, perfectly normal spiral and elliptical galaxies. Take the galaxy known as MCG plus 0102015, a spiral galaxy that looks as if it should be in a rich galactic neighborhood, not stranded in the ultimate cosmic desert. This presents a direct contradiction. Our standard model of galaxy formation is hierarchical, a bottom-up process where small clouds of gas and dark matter merge and clump together in dense environments, eventually building large galaxies. But here, in a region devoid of the raw materials and gravitational interactions needed for that process, fully formed galaxies exist. How did they get there? One compelling theory suggests these isolated islands are ancient relics. They could be survivors from a much earlier epoch, galaxies that formed when the universe was far denser, and then were left behind as the space around them expanded into a void. Another, more radical idea is that they formed in total isolation through a process we do not yet understand, a secret of star formation that only reveals itself in the most extreme environments. The strange normalcy found within such extreme emptiness forces us to question the very foundations of cosmic structure, leading us to wonder if other constants we rely on are truly unwavering. This push and pull between cosmic titans reveals a startling truth. Our journey through the cosmos is not guided by a single destination, but by a complex interplay of forces, a grand cosmic ballet where emptiness can be as influential as mass. While the Great Attractor pulls us toward it, another, more subtle force is simultaneously pushing us away. This is the Dipole Repeller. Imagine a vast cosmic hill, and our local group of galaxies is a ball slowly rolling down its slope. The Dipole Repeller is the high ground we are rolling away from. It is not a physical object, but an immense volume of space so profoundly empty that its gravitational influence is effectively negative. Cosmologist Yehuda Hoffman and his team identified this repeller by meticulously mapping the flow of thousands of galaxies. They realized the motion of our Milky Way, and its neighbors could not be explained by the pull of the Great Attractor alone. Something was also shoving us from the opposite direction. This concept fundamentally challenges a basic assumption about gravity, that it is only an attractive force. How can nothing push something? The answer lies in the large-scale structure of the universe. In a region dense with galaxies, gravity pulls inward. But in a vast void like the Dipole Repeller, the lack of matter creates a gravitational hill. Surrounding matter, including our own galaxy, naturally flows away from this underdense region toward the denser areas of space. It is the cosmic equivalent of water seeking its own level, with galaxies flowing from emptiness into crowded hubs. This reveals that voids are not passive absences. They are active players, sculpting the paths of galaxies across billions of light years. The existence of the Dipole Repeller forces us to see the universe not as a static collection of objects, but as a dynamic fluid, constantly in motion, shaped as much by what is not there as by what is. This intricate dance of attraction and repulsion, of something and nothing, points toward an even deeper mystery: the nature of the invisible fabric that governs it all. This intricate dance of cosmic forces leads to a startling possibility, one that hits closer to home than any distant void or attractor. We might be living inside the anomaly. Our entire local universe, a sphere 2 billion light-years across centered on the Milky Way, appears to be significantly emptier than the cosmic average. This is the KBC void, named for the astronomers Keenan, Barger, and Quie who identified its signature. The discovery forces a profound question about our place in the cosmos. Are we in a special, underdense region, a vast cosmic bubble of nothingness? This is not a small local quirk. The scale is staggering, encompassing thousands of galaxies, yet it still contains far less matter than it should. Its existence directly challenges one of the most fundamental pillars of modern cosmology, the cosmological principle. This principle states that on sufficiently large scales, the universe should look roughly the same in every direction and from every location, a homogeneous and isotropic cosmic fabric. But if we are sitting at the center of a billion light-year-wide bubble, then our viewpoint is fundamentally skewed. We are not in a typical place at all. This local anomaly has real consequences, potentially unraveling one of the biggest mysteries in astronomy today, the Hubble tension. This is the puzzling disagreement between two methods of measuring the universe's rate of expansion. One method uses the ancient light of the cosmic microwave background, while the other uses relatively nearby supernova and stars. The values do not match. If we are inside a giant void, it could explain the discrepancy. The gravitational pull of all the missing mass around us would subtly alter the apparent brightness and recession speeds of nearby galaxies, throwing off our local measurements. We would be misreading the universe's expansion from a flawed vantage point. This forces astronomers to confront an unsettling idea. What if dark energy, the mysterious force driving cosmic acceleration, is not a constant property of space everywhere? What if its apparent strength is just an artifact of our location inside this immense cosmic bubble? The KBC void suggests that our entire understanding of the cosmos could be filtered through a lens of local emptiness, a subtle distortion that makes us question everything we think we know about the universe's ultimate fate. This idea of a local cosmic bubble pales in comparison to a motion that encompasses the entire observable universe. Galaxy clusters, the largest gravitationally bound structures we know, are caught in a mysterious, coherent stream. They are all moving in the same specific direction at inexplicable speeds, as if pulled by a force that lies beyond the edge of everything we can see. Astronomers call this the dark flow. It was discovered not by watching the galaxies themselves, but by observing how they interact with the oldest light in the cosmos. Researchers led by Alexander Kashlinsky studied the cosmic microwave background as it passed through enormous clusters of galaxies. This interaction, known as the kinematic Sunyaev-Zeldovich effect, creates a subtle shadow that reveals the cluster's velocity. The data showed something that should be impossible. These clusters, scattered across billions of light years, are all streaming together. This is not the random motion of cosmic expansion. It is a directed flow, a current in the cosmic ocean pointing towards something we cannot see. The standard model of cosmology rests on a key principle, that the universe is largely uniform and isotropic. This means no preferred direction should exist on such a colossal scale. The dark flow directly defies this. It suggests that something of unimaginable mass, a structure or gravitational source that formed before the period of cosmic inflation, is exerting its pull from outside our observable bubble. What could possibly be large enough to tug at the entire visible universe? One radical explanation points to a gravitational tug from a neighboring universe in a vast multiverse. The fabric of reality itself may be textured with other cosmic domains, and their immense gravity could be leaking into our own, creating this coherent drift. If confirmed, the dark flow would be the first empirical evidence of something beyond our cosmic horizon, a shadow from a realm we were never meant to see. This profound mystery forces us to confront the ultimate question: is our universe truly alone? Or are we just one island in an infinite archipelago of reality? This directional pull on the largest scales is echoed by a pattern in the universe's oldest memory. The cosmic microwave background is the first light ever released, a fossilized snapshot of the cosmos when it was just 380,000 years old. According to our most fundamental principles, this afterglow should be a random, isotropic tapestry, with hot and cold spots scattered in every direction without any preferred alignment. It should show no more structure than the static on an old television screen, but it does. Cosmologists have discovered a strange, large-scale alignment in this ancient light, a pattern so unnerving it was nicknamed the axis of evil. This is not a malevolent force, but a statistical ghost in the machine, a series of correlations that suggest the universe has a fundamental orientation. The anomalies are found in what are called the quadrupole and octupole moments, which are essentially the ways the temperature fluctuations are organized on the largest scales. Instead of being randomly oriented, these patterns appear to be aligned with the plane of our own solar system, the ecliptic. This is deeply unsettling. Why would the structure of the entire observable universe be linked to the insignificant plane of our local planetary neighborhood? It is as if you drew a map of the entire Earth and found that all the continents were subtly aligned with the floor of your own living room. The implication is profound. It suggests a preferred direction in the cosmos, a fundamental skew that contradicts the cosmological principle's assertion that the universe has no center and no special direction. Cosmologist Kate Land was among those who highlighted this eerie alignment, forcing the field to confront its implications. One possible, mind-bending explanation is that this pattern is not a flaw in the data, but a fossil. It could be the imprint of a universe that existed before our own Big Bang, a cosmic structure whose gravitational influence has been imprinted onto our CMB. Another theory suggests the universe may have a complex topology, like a hall of mirrors on a cosmic scale, where space wraps around itself in a way that creates these observed correlations. The axis of evil forces us to ask whether the randomness we assume is a bedrock of reality might be an illusion, pointing instead to a deeper, hidden architecture woven into the fabric of space-time. The unsettling idea of a cosmic axis leads us to a more intimate mystery, the true shape of our own home. For decades, we believed our Milky Way was part of the Virgo Supercluster, a simple island of galaxies in the void. That map was wrong. Our true cosmic address is within the Laniakea Supercluster, a name from Hawaiian meaning immense heaven. This is not just a larger cluster, it is a vast cosmic watershed, a continent of space where every galaxy flows like a river toward a common gravitational sea. Astronomer R. Brent Tully and his team redefined our place in the cosmos by tracing this flow. They realized that static maps based on density were misleading. What truly defines a supercluster is motion, the shared destiny of galaxies pulled by the same gravitational anchors. At the heart of Laniakea lies the Great Attractor, the gravitational pivot around which our entire local universe revolves. The boundaries of this immense heaven are not solid walls you could touch. They are the points where one gravitational basin ends and another begins, the continental divides of the cosmos. Where the pull of Laniakea weakens, the influence of our neighbor, the even larger Shapley supercluster, takes over. This redefines the universe from a collection of static islands into a dynamic, flowing web. Galaxies stream along invisible filaments of dark matter, the hidden skeleton that dictates the structure of everything we see. So where exactly does our gravitational domain end? The answer is not a fixed line but a shifting frontier of competing influences, a place where the cosmic tides ebb and flow. Mapping these boundaries is like trying to trace the edge of a vast weather system, revealing the fundamental forces that have sculpted the universe since the beginning. This flowing reality suggests that even the largest structures are in constant motion, a concept that finds its ultimate expression in the most violent events imaginable. This same ancient light holds a specific chill that refuses to fade. The cold spot is not just another fluctuation in the cosmic microwave background. It is a colossal anomaly, a patch of sky so profoundly cold that it stands out as a statistical ghost in the machine. According to our most precise models of the Big Bang, a region this large and this frigid should not exist. It is a cosmic bruise that our standard theories cannot explain. For years, the leading hypothesis pointed to a cause we have already encountered, the Eridanus Supervoid. The idea was that this billion light, ear-wide emptiness could drain the energy from light passing through it, creating the cold spot we observe, but the math never quite added up. The void is immense, but it is not quite immense enough to account for the sheer depth of the cold. The temperature deficit is simply too great. This leaves cosmologists with a troubling puzzle. If a supervoid cannot fully explain it, then what can? Enter one of the most radical proposals in modern cosmology. Theoretical physicist Laura Mersini-Houghton has suggested the cold spot is not a void at all, but the imprint of a cosmic collision. In her model, our universe is just one bubble in a vast multiverse. In its earliest moments, it may have gravitationally brushed against a neighboring cosmic domain. That brief, unimaginable encounter would have left a scar on the fabric of our reality, a permanent cold spot in its first light. This is not just a wild idea. It is a testable hypothesis. If the cold spot is a multiverse signature, it should be surrounded by other, subtler anomalies in the cosmic background radiation, a specific pattern of hot and cold rings. While some studies have found hints of this structure, the evidence remains controversial. The debate forces a fundamental question. Is this frigid patch a rare statistical fluke, a one-in-a-million random variation that just happens to exist in our sky? Or is it a cosmic defect, a crack in the foundation of our universe pointing toward a deeper, more complex reality? The cold spot challenges the very limits of our most successful cosmological model, pushing us to look for other ghosts in the cosmic machine, anomalies that might reveal the true texture of reality. Even the vast continent of Laniakea is merely a single thread in a tapestry of unimaginable scale. We have pushed our observations to the absolute limit of the observable universe, and what we found there shatters our concept of cosmic structure. The Hercules Corona Borealis Great Wall is not just a large object. It is the largest single thing humanity has ever identified. This colossal filament of galaxies stretches across an almost incomprehensible 10 billion light-years, a structure so vast it would take light, the fastest thing in the universe, nearly 3/4 of the entire age of the cosmos, to travel from one end to the other. Its discovery by a team led by astronomer Istvan Horvath was a moment of profound reckoning for cosmology. It directly confronts one of our most cherished principles, the cosmological principle, which states that on the largest scales, the universe should look roughly the same everywhere. This principle sets a theoretical upper limit on how big structures can become before the universe starts to look lumpy and uneven. The Great Wall appears to violate that limit. It is not a random clustering of galaxies, but a coherent, gravitationally bound network of galaxy clusters and superclusters. A cosmic continent that makes our local Laniakea look like a small town. How could such an immense structure possibly form in the 14 billion-year history of our universe? The processes of gravity acting on normal and dark matter simply should not have had enough time to assemble something on this scale. It is like finding a single skyscraper that spans an entire continent, a construction project that defies the known laws of physics and time. This forces a radical question. Does the Hercules Corona Borealis Great Wall mean the universe is not as uniform as we thought? Is it a statistical fluke, a 1 in a trillion chance that we happen to see this particular overdensity from our vantage point? Or is it evidence that the initial conditions of the Big Bang were far more textured and irregular than our models allow, seeding the cosmos with primordial imbalances that grew into these impossible giants? The existence of this wall tells us our maps of the cosmos are still primitive sketches, and that the true architecture of reality may be built on a scale we are only just beginning to perceive. Long before the Hercules Corona Borealis Great Wall redefined scale, another cosmic leviathan held the title. The Sloan Great Wall is a sprawling cosmic metropolis, a filamentary structure of galaxies stretching over 1.3 billion light-years. Discovered within the vast data of the Sloan Digital Sky Survey, this wall is not a simple barrier but an intricate, three-dimensional web of galactic clusters and lonely voids. It provides our most detailed map of how the universe builds its largest structures. Within this web, you find gravitational anchors like the Shapley concentration, a supercluster so massive it exerts its own powerful pull on the entire local universe. The existence of such a complex and immense structure so early in cosmic history presents a direct challenge. Our standard models of gravitational collapse, acting on a universe expanding at a uniform rate, struggle to explain how matter could have clumped together on such a staggering scale in the time available. The Sloan Great Wall is not an anomaly, it is a template. Its intricate architecture, a frozen snapshot of the cosmic web, acts as a fossil. The specific pattern of its filaments and the density of its nodes are a direct echo of the quantum fluctuations that rippled through space in the first instant after the Big Bang. This immense structure asks a profound question. What do these specific blueprints tell us about the nature of the dark matter that holds it all together? The gravitational glue of dark matter must have specific properties, a certain coldness and stability, to allow for the formation of such a vast, coherent web. The Sloan Great Wall is more than a record-breaking object. It is a cosmic Rosetta Stone, its language written in galaxies and emptiness, waiting to be fully decoded. The immensity of these cosmic structures is anchored by an invisible substance, but one galaxy reveals this hidden skeleton in its most extreme form. In the heart of the Coma cluster, a dense gathering of galaxies, lies Dragonfly 44. At first glance, it is a cosmic ghost, a wispy smudge of light so faint it was only discovered with a specially designed telescope array. This galaxy has the same gravitational heft as our own Milky Way, a mass of nearly 1 trillion suns. Yet it emits a mere 1% of the light. Where our galaxy blazes with hundreds of billions of stars, Dragonfly 44 is a dim, sprawling phantom. The team led by astronomer Pieter van Dokkum calculated that a staggering 99.99% of its mass must be dark matter. This is not a galaxy with a dark matter halo. It is a dark matter halo with a few stars sprinkled in. The discovery shatters a fundamental assumption of galaxy formation, that visible stars and invisible dark matter are partners in a cosmic dance, their distributions closely linked. Here, that partnership has been severed. How could a galaxy acquire the gravitational pull of a Titan while producing almost no stars? One theory suggests it was a normal galaxy that had almost all of its gas and stars stripped away in a violent encounter within the crowded Coma cluster, leaving behind its dense, dark matter core. Another, more radical idea is that it was born this way. A failed galaxy that never managed to gather enough normal matter to ignite widespread star formation. Dragonfly 44 acts as a pure laboratory for dark matter, a place where its gravitational effects can be studied without the bright interference of normal matter. Its existence hints at a hidden population of similar ghost galaxies, a dark universe operating in parallel to our own. This phantom challenges us to ask if dark matter can form its own structures entirely independent of the stars we see, a secret architecture that has been shaping the cosmos all along. But the ghostly nature of Dragonfly 44 is just one piece of a much larger puzzle. The Fornax cluster, a nearby gathering of galaxies, presents a dark matter mystery that strikes at the very heart of our cosmological models. Here, in a cosmic neighborhood just 60 million light-years away, dark matter is not behaving as it should. According to our most successful simulations of the universe, known as the Lambda-CDM model, dark matter should pile up in a specific way at the centers of massive structures. It should form a sharp, dense peak, a cusp of invisible matter. Yet when astronomers pointed powerful telescopes like the Very Large Telescope toward the cluster's central galaxy, NGC 1399, they found something completely different. The dark matter was not concentrated in a sharp spike. Instead, it was spread out, forming a soft, low-density core. This is the core cusp problem, and it is a direct challenge to the standard dark matter paradigm. How can this be? If our simulations are correct, gravity should have compressed the dark matter into a dense, central cusp over billions of years. The fact that we see a soft core suggests that something is preventing this collapse. One compelling idea is that dark matter particles are not the simple, collisionless ghosts we assume them to be. Perhaps they can interact with each other through some unknown force, bouncing off one another and preventing a dense center from forming. This self-interacting dark matter would fundamentally change our understanding of the universe's invisible skeleton. Alternatively, the soft core might be evidence that we have gravity itself all wrong. Theories like modified Newtonian dynamics propose that what we attribute to dark matter is actually a modification of the laws of gravity on large scales. In this view, the soft core in Fornax is not a puzzle to be solved, but a prediction of a different set of physical laws. The Fornax cluster has become a critical laboratory, a place where we test the fundamental properties of the universe's dominant substance. Does its gentle core reveal a hidden sociability among dark matter particles, or does it force us to rewrite the rules of gravity? Each observation sharpens the question, pushing us to look deeper into other galactic clusters, searching for the subtle signatures that will finally unravel this cosmic secret. The Fornax cluster's gentle core presents a puzzle, but another cosmic collision offers a far more direct form of proof. The Bullet cluster provides a snapshot of two galaxy clusters caught in a violent merger, a cosmic car crash on the grandest possible scale. When these immense structures collided, their individual components behaved in radically different ways, creating a perfect natural experiment. The vast clouds of hot, X-ray emitting gas, which constitute most of the normal baryonic matter, slammed into one another. This created immense friction, slowing the gas down and sculpting the distinctive bullet-shaped shockwave that gives the cluster its name. But something else did not slow down. Using the subtle distortions of gravitational lensing, where the cluster's gravity bends light from background galaxies. Astronomers mapped the true mass distribution. They found that the bulk of the mass, the invisible dark matter, had sailed right through the collision. It was completely unaffected by the crash, leaving the visible gas lagging far behind. This observation, made by teams using the Chandra X-ray Observatory and the Hubble Space Telescope, was a landmark moment in cosmology. It provided the most direct visual evidence that dark matter is real, and that it behaves as a collisionless substance, interacting with itself and normal matter almost exclusively through gravity. This single observation ruled out a whole class of modified gravity theories that attempted to explain cosmic motions without invoking dark matter. If gravity alone were at work, the lensing effect would have followed the visible gas, not separated from it. Yet this triumph of detection opens a deeper mystery. What are the precise properties of these dark matter particles that allow them to pass through each other and everything else without a trace? The bullet cluster acts as a particle accelerator the size of the universe, showing us what dark matter does, but not what it is. It confirms its existence while deepening the enigma of its identity, a quest that now pushes scientists to consider even more exotic and elusive candidates. This fundamental disagreement strikes at the heart of cosmology, creating a rift in our most basic measurement of the cosmos. We call this the Hubble tension, and it is a crisis of precision. Two different methods for measuring how fast the universe is expanding, both incredibly accurate, are giving us answers that stubbornly refuse to agree. One method looks back to the universe's infancy, studying the faint afterglow of the Big Bang, the cosmic microwave background. This gives us a reading of the expansion rate from a time when the cosmos was just 380,000 years old. The other method uses cosmic lighthouses in our local universe, pulsating stars called Cepheid variables, and brilliant stellar explosions known as Type 1, a supernova. These give us a measurement of the expansion rate today. According to our standard model of cosmology, lambda CDM, these two numbers should line up perfectly. They do not. The local universe appears to be expanding about 10% faster than the early universe data predicts. Nobel laureate Adam Rees and his team, who helped discover the acceleration of the universe, are now at the forefront of this puzzle, meticulously cross-checking the data from the Hubble and James Webb Space Telescopes. The discrepancy persists. This is not a small error bar, it is a persistent and significant gap. What could be causing it? The most exciting possibility is that our model is missing a crucial piece of physics. Perhaps a strange, early form of dark energy gave the young universe an extra kick. Maybe exotic, unknown types of neutrinos flooded the early cosmos, altering its expansion history. Or dark matter itself might not be a simple, stable substance, but something that changes its properties over billions of years. Each of these ideas would force us to rewrite the textbooks. The Hubble tension forces a profound question: are the constants of nature truly constant? Could the fundamental forces or the properties of particles have been different in the distant past? If the expansion rate is not what we think, then our entire timeline for the universe's evolution, from the first stars to the fate of all galaxies, could be wrong. This rift is more than a statistical anomaly. It is a direct challenge to our understanding of cosmic history, suggesting that the universe is hiding a deep and dynamic secret within its accelerating frame. While the Hubble tension questions our cosmic timeline, another mystery arrives at nearly the speed of light itself. Ultra-high-energy cosmic rays are the most energetic particles in the universe, subatomic bullets traveling from the deepest voids of intergalactic space. Their existence defies a fundamental prediction made over 50 years ago, known as the GZK cutoff. Physicists Kenneth Greisen, Georgy Zatsepin, and Vadim Kuzmin calculated that particles accelerated to such incredible energies should not be able to travel vast cosmic distances. Their reasoning was simple yet profound. The universe is not empty, it is filled with the faint afterglow of the Big Bang, the cosmic microwave background. A proton traveling at near light speed, with an energy millions of times greater than anything produced in the Large Hadron Collider, would inevitably collide with these background photons. Each collision would be a hammer blow, sapping the proton's energy until it fell below the theoretical cutoff. According to their math, these cosmic cannonballs should never reach Earth from sources beyond our local galactic neighborhood. But they do. Massive observatories like the Pierre Auger Observatory in Argentina have repeatedly detected these forbidden particles. They slam into our atmosphere with the force of a well-thrown baseball, all their energy concentrated into a single subatomic point. The detection is undeniable, but their origin is a profound enigma. These ultra-high-energy rays do not point back to brilliant quasars or colliding galaxies. They seem to arrive from the darkest, most empty patches of sky, regions devoid of any known celestial powerhouse. How is this possible? What kind of cosmic accelerator is powerful enough to launch these particles and invisible enough to hide in plain sight? The leading suspects are active galactic nuclei, where supermassive black holes eject jets of matter at relativistic speeds, or perhaps immense shockwaves from galaxy cluster mergers. Yet even these colossal events struggle to explain the observed energies. The mystery deepens with a strange correlation. While many rays come from nowhere, a statistical handful appear to align with the large-scale cosmic web, the filamentary structures of galaxies and dark matter. This suggests their sources are not random, but are woven into the fundamental architecture of the universe, operating by physics we have yet to discover. These anomalous particles are messengers from the most extreme environments in existence, carrying encrypted information about forces and energies we cannot hope to replicate. They are a direct challenge not just to astrophysics, but to the very laws of particle physics as we know them. These faint gamma-ray structures are a ghostly echo of our galaxy's violent core. The Fermi bubbles tower over the Milky Way, two colossal lobes of hot gas stretching 25,000 light-years above and below the galactic plane. For all their immense size, they remained completely hidden from view until the Fermi Gamma Ray Space Telescope revealed their faint, high-energy glow. They are a permanent monument to a cataclysm we missed, a testament that our quiet, spiral galaxy has a far more explosive past than we ever imagined. What colossal force could have forged these structures? The prime suspect is our own supermassive black hole, Sagittarius A star. While it is relatively quiet today, it may have experienced a violent feeding frenzy in the past, devouring a massive cloud of gas or even a star. This feast would have unleashed twin jets of energy and matter, inflating these gigantic bubbles with ultra-fast particles. An alternative theory points to a different kind of violence, not from the black hole, but from a frenzy of star birth. A sudden, intense wave of star formation near the galactic center could have produced a flood of radiation and countless supernova explosions, their combined stellar winds blowing these enormous cavities. The true power of the Fermi bubbles lies not just in their origin, but in their ongoing influence. They are a masterclass in galactic feedback, the process by which energy from the core regulates the entire galaxy's life cycle. The bubbles act like a galactic thermostat. The energy they pump into the halo around the Milky Way helps prevent vast reservoirs of cool gas from falling back into the disk. Without this feedback, that gas would fuel an uncontrollable firestorm of new star formation, potentially burning through the galaxy's fuel supply too quickly. This reveals a delicate balance, where the galaxy's violent heart helps to maintain its stable spiral structure. So how often does our galaxy experience these outbursts? The bubbles are estimated to be a few million years old, a mere blink in cosmic time. This suggests that such cataclysmic events are not rare, but a regular part of a galaxy's life cycle. We may be living in a brief period of calm between galactic tempests. The Fermi bubbles force us to see our home not as a serene island universe, but as a dynamic engine that periodically erupts, its core activity written in invisible light across the sky. Our galaxy is about to catch a piece of its own past. The Smith Cloud is a colossal stream of hydrogen gas, a cosmic river millions of times the mass of our Sun, racing toward the Milky Way's disk at nearly 700,000 miles per hour. It is a returning exile, a fragment of our own galactic system that was violently ejected some 70 million years ago and is now completing its immense orbit. This homecoming is far from gentle. It is a high-velocity collision that will slam into the galaxy, likely triggering spectacular firestorms of new star formation. For decades, astronomers assumed such high-velocity clouds were pristine building blocks left over from the universe's formation, falling into galaxies for the first time. The Smith Cloud shattered that assumption. When scientists used the Hubble Space Telescope to analyze its chemical composition, they found the key. The cloud is rich in sulfur, a heavy element forged in the hearts of massive stars. This sulfur fingerprint proved the cloud was not a primordial visitor, but a recycled part of our own galaxy, a piece of the galactic disk that was somehow torn away and is now falling back. This discovery raised an immediate question. How did this fragile cloud of gas survive its multi-million-year journey through the violent, tumultuous halo of the Milky Way? A cloud of pure gas should have been ripped apart by gravitational tides or shredded by collisions with other material. The answer came from mapping its motion. The path and structure of the Smith Cloud indicated it was wrapped in a protective cocoon of dark matter. This invisible halo acted as a gravitational shield, holding the gaseous core together against all the forces that sought to destroy it. This is a profound revelation. We have always pictured dark matter as a vast, diffuse halo encompassing the entire galaxy. The Smith Cloud suggests that smaller, self-contained clumps of dark matter can also exist, acting as protective sheaths for wandering celestial objects. What galactic event could have been powerful enough to launch not just a cloud of gas, but its own private anchor of dark matter? The most likely culprit is a close gravitational encounter with a massive, dense object, perhaps a dark matter subhalo passing through the galactic disk, kicking this material out into the void. The cloud's eventual return illustrates a fundamental cycle of galactic life, a process of ejection and reaccretion that helps replenish the raw materials for future generations of stars. The Smith Cloud is more than a returning traveler. It is a living fossil, a dynamic probe of the invisible dark matter structures that shape our galaxy's evolution from within. This returning river of cosmic gas finds a stunning parallel in the heavens above, a structure so vast it paints a scar across nearly half of the visible sky. Trailing behind the large and small Magellanic clouds, our most prominent satellite galaxies, is the Magellanic Stream. This is not a mere wisp of dust, but a colossal river of neutral hydrogen gas, a filamentary tail torn from the dwarfs themselves as they dance through the Milky Way's gravitational field. For decades, the textbook explanation seemed simple enough. Tidal forces, the same gravitational pull that creates ocean tides on Earth, were thought to be slowly shredding the smaller galaxies. Combined with ram pressure stripping, the resistance felt as they plow through the thin gas of our galaxy's halo. This process appeared sufficient to explain the stream's existence. Yet, as our simulations grew more sophisticated, a problem emerged. The sheer mass and intricate, shredded morphology of the stream were far more complex than our models could easily reproduce. It was as if we were trying to explain the Grand Canyon with only a gentle stream of water. The scale was all wrong. Then came a revelation from detailed spectroscopic observations. The gas within the Magellanic Stream is not just neutral, It is also glowing, ionized by an external source. The culprit appears to be our own galaxy's extended atmosphere, its hot, gaseous corona. This invisible halo of million-degree plasma is actively cooking the stream, stripping electrons from its atoms and fundamentally changing its chemistry and structure as it falls toward us. This discovery turns a simple narrative of gravitational theft into a far more dynamic and destructive interaction. The galactic corona is no longer a passive backdrop. It is an active participant, shaping and eroding the material it will eventually consume. This forces a critical re-evaluation of the corona's very properties, its density, temperature, and extent, which are all now called into question. So what is the ultimate fate of this immense structure? The Magellanic stream is not a permanent feature. It is a cascade of raw material, a direct pipeline of fuel currently falling into the Milky Way. Over the next few 100 million years, this gas will slam into our galaxy's outer disk, likely igniting bursts of new star formation, seeding the future with suns born from captured remains. This ongoing accretion event provides a rare, real-time laboratory. We are witnessing the process of galactic growth and evolution not in a distant snapshot, but as it unfolds, revealing the violent and intricate interplay that governs even the smallest of galactic groups. While our galaxy feasts on incoming streams of gas, the farthest gravitational reach of our own sun remains a ghostly and unseen territory. The Oort cloud is a hypothetical, spherical shell of icy planetesimals, a vast reservoir of frozen primordial material stretching nearly a light-year from the sun. This is not a flat disk like the asteroid belt, but an immense, thick-skinned bubble enveloping our entire solar system. Its existence is not something we can photograph, for its countless objects are too distant and faint, mere specks of rock and ice in the profound dark. Instead, we infer its reality from the paths of long-period comets, those spectacular, icy visitors that plunge into the inner solar system on orbits lasting millions of years. Each one is a messenger from this uncharted frontier, its elongated path pointing back to a gravitational source at the very edge of the sun's influence. This cloud is a cosmic attic, a deep freeze relic holding pristine building blocks from the solar system's formation 4.5 billion years ago. The true structure and population of this cloud, however, is one of astronomy's great unknowns. How many trillions of objects does it contain, and how are they distributed? Their delicate orbits are not static. They are perpetually tweaked by subtle external forces, the gentle but persistent pull of the Milky Way's gravity, what we call the galactic tide, and the occasional gravitational nudge from a passing star. These stellar flybys can act like a cue stick, dislodging comets from their icy slumber and sending them on a sunward plunge, or even stealing them away entirely. This makes the Oort cloud a dynamic and ever-changing borderland, a place where the sun's rule wanes and the galaxy's influence begins. Studying the comets that originate here is like reading pages from our own solar system's birth certificate, revealing the original composition of the protoplanetary disk. The grandest question this icy frontier poses is whether it is unique. Do all stars have their own Oort clouds? If so, these vast reservoirs could be the source of interstellar objects like Oumuamua, the first known visitor from another star system. The Oort cloud represents the final, unexplored chapter of our own cosmic backyard, a realm of whispers and shadows that holds the keys to our origins and our place in the galactic neighborhood. Far beyond the scattered disk of the Kuiper belt, in the frigid darkness where the sun is just a particularly bright star, a pattern emerges from the chaos. The most distant known objects in our solar system, small icy bodies like Sedna, follow strangely clustered orbits. These paths are tilted and aligned in a way that should not happen by chance, as if an unseen shepherd is guiding their motion. The gravitational signature points to a single, massive culprit, a hypothetical world astronomers call Planet 9. Proposed by Caltech researchers Konstantin Batygin and Mike Brown, this world is no Pluto. It is a super-Earth, a planet 5 to 10 times more massive than our own, tracing an immensely elongated path hundreds of times farther from the Sun than Earth. Its proposed orbit is so vast that a single year there could last 20,000 Earth years. Why has such a colossal world remained hidden? The answer lies in its staggering distance and faintness. At such remote reaches, the Sun's light is hopelessly dim, and a planet reflects almost none of it back toward our telescopes. We are not looking for a bright disk, but for the subtlest whisper of reflected sunlight against the blackness of intergalactic space. The search is a monumental game of celestial connect the dots. Using the skewed orbits of the small bodies it perturbs to triangulate its possible location in the sky. If it exists, its discovery would force a complete rewrite of our solar system's history. How did a planet this large end up in such a distant, eccentric orbit? It may have been flung outward during the solar system's violent youth by a gravitational kick from Jupiter or Saturn. Or, in a more radical scenario, it could be an exiled world, a rogue planet that was captured by our Sun's gravity as it drifted through the galaxy. This single, unseen object holds the potential to reveal that our familiar planetary neighborhood was once a place of dramatic upheaval and planetary rearrangement. Its gravitational influence might even explain the peculiar tilt of the Sun's axis. The hunt for Planet 9 is a stark reminder that our own cosmic backyard remains deeply unexplored, and that the most profound discoveries may still be waiting in the perpetual twilight at the edge of our own star's domain. The strange clustering of orbits at the solar system's edge finds its echo much closer to home, in the vast disk of icy bodies beyond Neptune. The Kuiper belt is far more than a simple repository of frozen leftovers. It is a cosmic crime scene where the evidence points to a violent and dynamic past. The orbits of some of its most distant inhabitants, like the dwarf planet Sedna, are profoundly strange. They are not neat, circular paths close to the solar system's flat plane. Instead, they are highly elongated, stretching hundreds of astronomical units from the Sun before swinging back in. And they are dramatically tilted. These objects are effectively detached from the direct gravitational influence of the giant planets we know. Their very existence is a puzzle that standard models of our solar system's formation cannot easily solve. If Neptune and the other giants were the only major players, how did these icy bodies get shepherded into such extreme and isolated orbits? The answer seems to lie in a period of great upheaval during the solar system's infancy. One compelling theory suggests a stellar flyby, a close gravitational encounter with another star in the Sun's birth cluster. This passing star could have acted like a gravitational whip, yanking these distant objects into their current strange paths and tilting their orbits. Another, as we have seen, points to the persistent tug of an unseen massive planet. The Kuiper belt's anomalous orbits are therefore fossil records, celestial hieroglyphs that tell a story of a time when our cosmic neighborhood was a far more chaotic and crowded place. By meticulously mapping these paths, astronomers are performing a form of celestial archaeology, piecing together the gravitational events that sculpted our solar system's outermost frontier. This region is not a serene relic, frozen in time. It is an active history book written in the language of motion and gravity, challenging our perception of a quiet and orderly planetary system. Our solar system is currently adrift in a cosmic cavity, a 1,000 light-year-wide sphere of million-degree plasma known as the local bubble. We are not permanent residents here, but temporary travelers, our Sun merely passing through a structure forged by ancient stellar violence. This entire region was carved out by a succession of at least 15 supernova explosions, cataclysmic stellar deaths that occurred over the last 10 to 20 million years. These titanic blasts swept up the dense, cold gas that once filled this volume of space, compressing it into the complex, glowing filaments of gas and dust that now trace the bubble's intricate boundaries. We can see the aftermath of this process in the young, brilliant star-forming regions that line the bubble's edge, such as the Scorpius-Centaurus association. These stellar nurseries were likely triggered when the expanding shockwaves from the supernova squeezed interstellar clouds, collapsing them into new generations of stars. This reveals a profound cycle of destruction and creation, where the death of old stars directly seeds the birth of new ones, sculpting the galactic environment on a grand scale. But how does this ancient violence affect us today? The local bubble is not an empty void. It is filled with a thin, searing hot wind of ionized gas that exerts a constant pressure on our sun's own protective magnetic bubble, the heliosphere. This interaction directly influences the size and shape of our solar system's first line of defense against interstellar space. Perhaps more critically, the bubble's low density acts as a partial shield. Cosmic rays, high-energy particles from across the galaxy, are somewhat scattered and diluted as they travel through this cavern, subtly modulating the amount of radiation that reaches our inner solar system. This means the violent deaths of those ancient stars millions of years ago created a temporary, more protected environment, a habitable cavity that may have indirectly influenced the conditions for life to arise and thrive on Earth. Our local galactic neighborhood is not a static backdrop. It is a dynamic and evolving ecosystem, its history written in supernova fire, and its present state a fleeting moment of calm within a storm of stellar evolution. These repeated cosmic anomalies are not isolated oddities, but a chorus of dissent against our most fundamental assumption about the universe. The cosmological principle has been the bedrock of modern cosmology for a century. The simple, elegant idea that on the largest scales, the universe is smooth and has no preferred direction. It is the reason we can extrapolate from our single vantage point and assume that observers in a distant galaxy would see a cosmos roughly similar to our own. Yet the evidence we have gathered tells a different, far more interesting story. We find ourselves pulled by an invisible great attractor, surrounded by a billion light-year-wide void, and living in the shadow of cosmic walls that defy theoretical size limits. The universe, it seems, has a texture, a grain, and a structure that is anything but uniform. This is more than a collection of statistical flukes. It is a pattern of defiance. Each giant structure and anomalous flow chips away at the foundation of the standard model of cosmology, lambda CDM, which relies on this principle of large-scale uniformity to explain the universe's evolution. If these structures are real and not mere illusions of our perspective, then our entire cosmic history must be rewritten. We are forced to ask if the initial conditions of the Big Bang were far more complex and lumpy than we ever imagined, seeding the cosmos with primordial imbalances that grew into the giants we see today. Or perhaps the dark energy driving cosmic acceleration is not a constant force but a dynamic field that varies across space, creating pockets of different density and motion. The implications are staggering, suggesting that our universe is not a simple, homogeneous expanse, but a complex and perhaps even finite structure with a discernible architecture. Are we on the brink of a paradigm shift, where the smooth cosmic canvas gives way to a tapestry of stunning and unpredictable complexity? The answer lies in the next frontier of discovery, where the darkest secrets of the cosmos await. Our journey through these 23 cosmic frontiers reveals a universe that refuses to be tamed by our textbooks. From the invisible pull of the Great Attractor to the frozen whispers of the Oort cloud, each mystery peels back a layer of reality, exposing a cosmos of stunning complexity and profound strangeness. These are not mere curiosities. They are direct challenges to the foundational pillars of modern physics, questioning the uniformity of space, the nature of gravity, and the very identity of the dark components that govern our cosmic fate. Our current knowledge is like an ancient map, beautifully detailed in some areas, but with vast, blank spaces still boldly labeled "Here be dragons." This is not a failure of science, but its very essence. The pursuit of understanding these anomalies, these glorious dragons at the edge of the map, is what propels human curiosity forward. It is the engine of discovery. The astronomer Carl Sagan once reflected that somewhere, something incredible is waiting to be known. That sentiment echoes across every void and every unexplained flow, a reminder that the greatest discoveries likely lie just beyond our current horizon. We would love to hear which of these cosmic mysteries captivated you the most. Share your thoughts in the comments below, and if your curiosity is sparked, subscribe for more journeys to the edge of understanding. Wherever you are, keep looking up.